Let's now see more examples of elimination. So on the 2x2 system, I explained the issues and how to resolve them when you have infinitely many solutions, when you have a zero in the pivot. But you really see elimination, which by the way is called Gaussian elimination. I should probably write that. Gaussian elimination after Gauss. So you can really see what's going on a 3x3 system, and next week we'll see even different systems that don't have to be square, maybe 3x4 or 4x3 or 4x5. But the ideas are exactly the same. Okay, so first step is I'm going to write the augmented matrix that represents this system. My goal is to find the x, y, and z that satisfy the three equations simultaneously. So my system AX equals B is 2, 4, negative 2 in the first column, 4, 9, negative 3 in the second, negative 2, negative 3, 7 in the third, and I'm going to write B right next to them, 2, 8, 10. I don't know about you, but I tend to see better in a matrix rather than when I copy the X's and Y's and Z's all the time. So remember, we have row 1, row 2, row 3. Now, the first row, and in the first column of the first row, there is a non-zero number. So that is our candidate for the first pivot. Using that pivot, we need to eliminate everything underneath it. So I need to produce a 0 instead of that 4 in the second row, and I need to produce a 0 instead of the negative 2 in the third row. Since I will be using the first equation to eliminate in the second and in the third, I can do these operations simultaneously. Let's think about the operation for R2. So we need to have something like this. R2 minus some number times R1 needs to become the new R2. And then R3 minus some number times R1 needs to become the new R3. So observe the structure of these operations. You start with R2, you do something to it, and that becomes your new R2. You start with R3, you do something to it with another row, and then you write the result as a new R3. It's always going to be like that. Now, which row do I use to change R2 and R3? The row with the pivot. So this over here is the pivot row for elimination at this stage. So what number would work? I want to get a 0 in the first column in the second row. So the operation would be 4 minus something times 2 should equal 0. That's my goal. I'm trying to eliminate under the pivot. This makes it very obvious. So this is for R2. Makes it very obvious that in the box I should have a 2 here and 2 there. And then finally for R3, well, I have negative 2 minus something times 2 should be 0. Well, if I put a negative 1 in here, that's going to turn this second thing into a 2. So I'll have negative 2 plus 2 is 0. So this really should be a negative 1, or rather, the operation is R3 plus R1 into R3. I'm going to correct that to make it easier for computations. It just looks better. So sometimes we will have pluses, of course. All right, we didn't say anything about the first row, which means the first row stays the same. 2, 4, negative 2, 2. And then we apply the operation. So we know we need to have a 0 here. And then I have R2 with that 9. So I have 9 minus 2 times 4. That will give me a 1. Now I'm going to work in the third column. So I have negative 3 minus 2 times a negative 2. So that's negative 3 plus 4. That gives me a 1. Then I have 8 minus 2 times 2. And that gives me a 4. If you need to write down all these operations, please go ahead and do that. Now in the third row, I'm going to use the third and first. And all I need to do is add them up, so that's not really nice. 2 and negative 2 give me 0. 4 and negative 3 give me 1. Negative 2 and 7 is a 5. 2 and 10 is a 12. So now we reach this second form. It's a new matrix. And now we need to go into the second row and look at the first non-zero number. This non-zero number is in the second column, ideally where we wanted it, and that is the new pivot. So this is the second pivot. We want to use it to eliminate underneath. Now observe, this is quite interesting how this part really we know how to handle. We will not use the first equation anymore. Now the system from being 3 by 3 is reduced to 2 by 2. And as you might imagine, if we started with a big system, say 4 by 4, with the first elimination, you get to a system of size 3 by 3. With the next elimination, 2 by 2, and you're done. All right, now what is the next operation? So I want to use the second row to eliminate into the third row, and the operation is simply R3 minus R2 into R3. The answer, I'm going to write it right here. It is 2, 4, negative 2, 2. Now observe, I don't have an operation that goes into the second row, so I keep the second row as is. And then I have 0. 1 minus 1 gives me 0. 5 minus 1 gives me 4. 12 minus 4 gives me an 8, and I am done. I have my 3 pivots, the 2, the 1, and the 4, and I don't have any contradictions. So I can write the 3 equations. The first equation is 2x plus 4y minus 2z equals 2. The second equation is y plus z equals 4. And the last one is 4z equals 8. Now you see why we call this elimination. It's not just eliminating numbers, it's actually eliminating variables. So if you look at this first step right over here where we eliminate with the first pivot, what we're effectively doing is removing x from the second and third equations. So if you were to rewrite the system of equations, and maybe we should rewrite it, just so you guys can see it. So the system of equations for this matrix would be 2x plus 4y minus 2z equals 2. From the second equation, we have y plus z equals 4. And from the third equation, we have y plus 5z equals 12. You see, in the second and third equation, we no longer have x. So that first step of eliminating with the pivot that corresponds to x makes sure that our system becomes simpler. And now the second pivot serves to reduce this system so that we're using the second equation, we can eliminate y from the third equation to get the last system, which is now ready for back substitution. So using back substitution, we can solve the system. So from the last equation, we have z must be a 2. Then we use it in the previous equation. So in the second equation, we have y plus 2 now instead of z equals 4. This tells us that y must be 2. So we have z and we have y. Now we'll use these two to replace in the first equation, and we're going to get 2x plus 4 times, now instead of y I'm going to write 2, minus 2 times 2 for z equals a 2. Simplifying gives us, what do we have? So 2x equals, so we have 4 times 2 is 8. 8 minus 4 is 4. On the other side becomes negative 4, so this is negative 2, which means x must be negative 1. And we always like to write things in a vector form, so x, y, z, which is the vector x, equals negative 1, 2, 2. And again, just like in the 2 by 2 case, we started with a system ax equals b. We performed a bunch of elimination steps. So we performed elimination. And we ended up with a system ux equals c. So you see, the matrix at the end is what we call an upper triangular matrix because everything under the diagonal of the matrix is 0. So it just means that the upper triangle of the matrix A, or rather U, is non-zero. Or if there is something non-zero, is in the upper triangle. All right, let's look at another example. Something simple. So again, right away, I'm going to write my augmented matrix. 1, 1, 1, 1, 1, negative 1, 1, negative 1, 1. We know right away this is going to be easy. 7, 5, 3. Remember, the first pivot is the first non-zero of the first row. So with the first equation, we want to eliminate x from the second and the third equation. That's the point here. So we will have R2 minus R1 into R2 and R3 minus R1 into R3. The first row stays the same, so we just copy it down. In the second row, 1 minus 1 is 0. 1 minus 1 is 0. Negative 1 minus 1 is negative 2. 5 minus 7 is negative 2. In the third equation, we have 1 minus 1 is 0. Negative 1 minus 1 is a negative 2. 1 minus 1 is 0. 3 minus 7 is a negative 4. We're done with the first step. We have eliminated x from the second and the third equation, but now we have a problem. So we have a breakdown of elimination because this pivot position has a 0. So this says breakdown of elimination. And the reason for that is 0 in the pivot position. So at this point, we ask ourselves, are we able to fix this 0 in the pivot position? Are we able to fix this situation? What was the point? The point was in the first equation, we want to have x, y, and z showing up. In the second equation, we don't want to have any x's, but we want to have a y. In the third equation, we could have a z in the second equation. Z is not the point, but we want to have, if there is a y remaining, we want that y to be in the second equation. Well, we have it in the third equation. So if we had started from the very beginning with these two equations in the opposite order, we wouldn't have this problem. Well, that just means that at this point, we can just exchange the second and third row. So R2 into R3 and R3 into R2, and that gives us the system 1, 1, 1, 7, 0, negative 2, 0, negative 4, 0, 0, negative 2, negative 2, and we are done. We have our upper triangular matrix U. We have our 3 pivots, so it is possible to solve the problem. Now we use back substitution. So we have from the first equation, x plus y plus z equals 7. From the second equation, 2y, negative 2y equals negative 4. Third equation says negative 2z equals negative 2. Using back substitution, we start at the bottom. It means that z equals 1. From the second equation, the second and third are really independent, but for the second equation, we have y equals a 2. And then using these two results, we go into the first equation, and here we have x plus 2 plus 1 is a 7, which tells us that x must equal 4. And we have our system solved. So this breakdown of elimination was not dangerous. We were able to recover. The solution is unique. Now in this case, we will have a breakdown of elimination that we will not be able to fix. Let's see what's going on here. The operations will be very similar because the matrix coefficients are similar, but not the same. Negative 1, negative 1, 1, 3. Again, we have our pivot and we need to eliminate underneath it because we only want x to be in the first equation, but not in the second or third. So we have R2 minus R1 into R2 and R3 plus R1 into R3. The first equation stays the same, the first row. Now we have 1 minus 1 is a 0, 1 minus 1 is a 0, negative 1 minus 1 is negative 2, 5 minus 7 is negative 2. Now we are adding. 1 and negative 1 is 0, 1 and negative 1 is 0, 1 and 1 is 2, 7 plus 3 is 10. Now, we try to find what's going on in the second row. Well, in the second row, the first the pivot position for y is 0. It is not possible to exchange rows because we have a 0 underneath as well. Now, here we have a breakdown of elimination because we have a 0 in the pivot position, which tells us that at best, we are going to have a system of equations that has infinitely many solutions. So there is no way we can get a unique solution. For a unique solution, we need to have 3 pivots. Here, we can at best have 2 pivots. So actually, it's not a problem. We can't really replace exchange rows. That doesn't solve anything because there is a 0 underneath as well. But let's see what happens if we just carry out the remaining elimination. So this would be the second pivot. Now we'll use that to eliminate underneath. We have R3 plus R2 into R3. Our goal is always to reduce the number of variables in the equations so that we can use back substitution. So the first and second rows stay the way they are. 0, 0, negative 2, negative 2. And then we add 0, 0, 0, 8. And this is the problem. Why is that the problem? Because if you write the equation, it says that 0 equals 8, and that's not possible. So we have the system is inconsistent. We get something like this, which means there is no solution. And it is not possible to recover from this failure of elimination. Now, few things that I did not mention, but I can at this point, just comments. If we start with a matrix A, let's at this point assume square matrix. Elimination, if elimination produces pivots in every row and every column, then A is invertible. Otherwise, A is not invertible. This is also called A is singular. Think of it as being single, being alone, doesn't have an inverse partner. And the columns of A are linearly dependent. What this means is that you could combine the columns of A in some way to get 0, but that way is non-trivial. So it doesn't mean you cannot multiply the rows, all the columns of A by 0 and get 0. That doesn't work. You have to multiply the columns of A, or it does work, but it doesn't count. You have to multiply the columns of A. You have to be able to multiply the columns of A by some non-zero numbers, and when you add them together, you get 0. Anyway, we'll talk about this more next week. Don't worry too much about invertibility. For today's lectures, I kind of want you to focus on being able to do elimination and back substitution. And in the lab today, I was talking about being able to describe your work. Well, these equations over here describe your work. Putting your pivot in a square describes your work. Telling me that the system is inconsistent and there is no solution and saying that's because 0 equals 8 is a description of your work. Similarly here, writing back substitution and showing me a little bit how you found it is already all I want. I don't need you to write me essays to describe your work. This is going to be very important, but we'll talk about that all of next week. All right, until next week, everyone.